So as we ended with on Wednesday, I want to walk through Dijkstra's algorithm. I've got a digraph with weighted edges. We made from this a weight matrix. And now my goal is to figure out the lowest weight from vertex 1 to other vertices, the shortest path to get here. To do that, I'm going to label each of the vertices. They get a permanent label, they get a temporary label. They get a permanent label when I have decided that this is the shortest path from 1 to it. They get a temporary label until then. But clearly, from starting at 1, doesn't cost me anything to go from 1 to 1. So that gets a permanent label. Everything else is temporary label based on the distance from 1 to it. Remember, if there is no edge arc from 1 to a vertex, that weight is infinite. So it's a cost of 7 to go directly from 1 to 2, a cost of 2 to go directly from 1 to 3, and I can't get directly from 1 to 4 or 5. I have permanent vertices labels. Right now, that's just 1. Everything else is in the temporary label pile. Dijkstra's algorithm proceeds iteratively. We find the vertex for which the temporary label is smallest. By the way, if no such thing exists, we have to stop. Label that permanent and move it to the permanent pile. But then go through and change the weights on the temporary ones by picking whichever is smaller, the current temporary label, or go to this vertex that you just moved first and add it into the path. All right, wait a minute. I want to do this for this graph with this matrix and this starting point. So we've done step 0. We've set up our starting points. Step 1, find the vertex in the temporary one with the smallest label. Smallest label up there is? So I'm going to make that the permanent label on vertex 3. So the first thing I do in step 1, I move 3 into the permanent pile. It's got a permanent label on it. Now, my new temporary pile consists of 2, 4, and 5. They still have their temporary labels. This step says I need new labels for all of those. I need a new label, L prime of 2, L prime of 4, and L prime of 5. And this is the minimum of the label that's already on 2, or the label we just came up with, plus the weight to go from vertex 3 to vertex 2. I got to go back to the matrix. How much does it cost me to go from vertex 3 to vertex 2? I can do that from the matrix. I can do it from the diagram. I have the matrix right here. To go from 3 to 2 costs me 3. The smaller of those is 5. That's my new temporary label. 5 is smaller than 7. That was easy. Do it again for label 4. Label 4 is the minimum of either the current label is infinity, or the label we just marked plus how much it costs to go from vertex 3 to vertex 4. What's the cost to go from 3 to 4? Which is smaller, infinity or 10? Yeah. The temporary label on 5 is the minimum of infinity or 2 plus the cost to go from vertex 3 to vertex 5. New labels. Repeat the setup. Okay, do it again. Which vertex in the temp pile has the smallest label? Vertex 2 this time. 2 goes into my permanent pile. My permanent pile now consists of 1 and 2 and 3. Over here, by the way, remember, the label on 1 is 0. The label on 3, that was 2. The label on 2 is now 5. And that's a permanent label. This means that my temporary set consists only of 4 and 5. I need new labels for those. The new temporary label for 4 is the minimum of the current label on 4, or the one we just labeled, plus the cost to go from there to 4. What's the cost to go from 2 to 4? Well, the smaller of those two is 6, no question about it. The temporary label on 5 is the minimum of the current label on 5, or the label we just made permanent plus the cost to go from 2 to 5. What's it cost to go from 2 to 5? Because you can't get there from here. Well, then the smaller one is 7. I have now successfully assigned new labels to all of my vertices. I made another one permanent, but I still have temps. Keep going. What new vertex becomes permanent? The one with the smaller temporary label. So now I change that label to be permanent. This means that my temporary set consists only of 5, and the new temporary label on 5 is either 6 or the label we just made permanent plus the cost to go from 4 to 5. What's the cost to go from 4 to 5? Oh, I made a copy error. Remember, we take the old, the label that was already on it, or the new label plus the cost. All right, well, that's 7. That's the only temporary temporary label. That's got to be the smallest temporary label. So step 4, move vertex 5 to my permanent set. My permanent set now consists of all of my vertices, and the permanent label on 5 is 7. I'm done. All 5 of my vertices have permanent labels. I've run out of temporary vertices, and my permanent vertex list is complete. I'm done. But what does this tell me? Let's go back to our digraph. These labels represent the shortest path and the distance from 1 to each of those vertices. How did I get there? Well, let's go through and write a digraph in the order we created our vertices. So I started with vertex 1, and the cost to go from 1 to 1 is 0. What vertex did I make permanent in step 2? Oh, sorry, technically in step 1. I made vertex 3 permanent. What did I make permanent in the next step? I'm writing down the weight and the edge directly from our old version of our digraph. Wait a minute, to go directly from 1 to 3 was 2. To go directly from 3 to 2 cost me 3. That total distance is 5. That's the shortest path to get to vertex 2. What was the next vertex we changed to be permanent? And the shortest distance to 4 is 6. Wasn't that an edge of weight 1? There's the shortest path from 1 to 6. I found it. Not only did I find it, I found the shortest distance, and I was able to find the shortest path. Then we created 5, right? And the shortest weight here is 7. We got that from here. We got that from here. We got that from here. This is where we went from 3 to 5. So the next edge that gets added is here, and there's the shortest path. That, ladies and gentlemen, that is nauseatingly tedious. However, it is codable. And it is actually fairly straightforward to code this. You will find lots of good examples of that code online. Dijkstra's algorithm is a big O of n squared algorithm based on the number of vertices. And that actually turns out to be really damn efficient. However, it's a little restrictive. First of all, I'm only starting with whichever vertex I picked as vertex 1. What if I don't want to know the shortest path from 1 to something? I want to know the shortest path from 5 to something. I've got to relabel all these vertices and do it again. Pardon my bluntness. No, I don't want to do that. So, two guys, Floyd and Warshall, came up with a method wherein we could use the matrix we created to keep track of the shortest distances. And we could create another matrix to keep track of the path separately. Now, problem number 1 is that the Floyd-Warshall algorithm is, I believe, big O of n cubed at best. So it's a lot more work. So if I was going to do exactly the same graph we just did, but I was going to do the Floyd-Warshall algorithm, I would need to start with that same matrix A. But I would need a second matrix, another 5 by 5, where each column in the second matrix is identical all the way down. This is our starting point for Floyd-Warshall. Now, I'm going to do an iterative procedure. And every time I do that, I'm going to change both of these matrices. So for the moment, I'm going to call this the starting point. I'm going to call this A0 and P0. Just put a little superscript inside parentheses on each one. if I find that there is a shorter path from vertex 1 to something other than directly listed here, I want to change A. And I want to change P to reflect, hey, you should go here first. Now, I'm going to write down the steps in the algorithm right now, and I'm going to tell you this is going to read like it's written in Swahili. That should be J minus 1 up here. There's an else after this if then. So this is the if, the first part. All right, wait a minute. What the hell does this say? Before I even get on to the else, let me figure out what this says. What this says is if going from vertex I to vertex K is smaller than or equal going from I to J plus J to K. Don't change anything. But if this is broken, then I'm better off going here first, aren't I? The else means I got to change something. We're better going the other way. So change the weight in matrix A to be the smaller thing. Isn't this what we did with our temporary labels? Hey, pick whichever one's smaller, the label that was already there or the label we just decided plus something else. So either don't change anything or give me the smaller label. Then I also have to change P. Change the label so it tells me, oh, no, don't go to K directly. Go to the thing in the J column instead. Remember, I am dealing with a 5 by 5 matrix. That means I am going to do this comparison right here 25 times to go through the first iteration. I got to do it all vertices. I got to do this n cubed times. I wrote it down. I wish I was lying to you when I tell you that this is 7 pages long. Not only am I never going to make you do this crap by hand, it took me about 2 hours to make sure I'd not made a mistake in here. Here we go. I want to build A1 and P1 from A0 and P0. So I'm going to compare AIK to AI1, A1K. Am I better off going from wherever I am to vertex 1 before going to the other destination? Should I go via vertex 1 instead of going directly? Is it any shorter? Yes or no? No. I did all 25 checks, and all 25 of them, the if went yes. Going directly is less expensive than going via vertex 1. So I made no changes. All right, now I have these two matrices. Now I'm going to say, wherever you are you better off going directly to the next vertex, or are you better going via vertex 2? I found one. I even wrote it in capitals. No. Aha. Going directly from 1 to 4, I can't get directly from 1 to 4. Remember, you know what my graph looks like. The same graph we were using for Dijkstra's algorithm. I can't go from 1 to 4. So it's cheaper to go from 1 to 2, followed by 2 to 4. So I'm going to take the infinity that was in 1, 4 and replace it with a 8. I did it again. Because going from 3 to 4 costs me 8. But going from 3 to 2 to 4 costs me 4. So let's replace that number with a 4. Now that just tells me what the new weights are. Notice what changed in P. The numbers that were 4s became 2s. I'm starting to track my path. I'm better off going via vertex 2 to get to 4. I'm better off going via vertex 2. And on and on and on we go until I get here. So I have now done all of the changing. I've done 5 iterations. I have my shortest weights. I have my shortest paths. We already worked out the shortest distance from vertex 1 to everything else, right? We did that with the Dijkstra algorithm. So let me go back to Dijkstra's algorithm for a second. In Dijkstra's algorithm, we said the cheapest way to get from vertex 1 to vertex 2 was to go from 1 to 3, 3 to 2. And it cost me 5. The cheapest way to go from vertex 1 to vertex 2 cost me 5. Notice this top row, 0, 5, 2, 6, 7. 0, 5, 2, 6, 7 are exactly the same weights we found in Dijkstra's algorithm. The shortest paths from 1 to something else. is the first row in matrix A5. How does P help me? P helps me figure out the path. I want to go from 1 to 2. From 1 to, where were we going? We were going from 1 to 2, yes. So I start in 1. And it says, oh, you want to go from 1 to 2, go to the second column. Is that a 2? Then you're not done traveling yet. You're at vertex 3. Go to row 3. Can you get to row 2? Yes. You just found the path. 1 to 3 to 2. You found the shortest path. 1 to 3 to 2. So I can use the matrix P to figure out the path. What's the cheapest path from 3 to 4? This is small enough that I can do it right off the picture, yes? What's the cheapest path from 3 to 4? It's got weight 4. How do I get there? Row 3, column 4. No, I got to go 2. Row 2, column 4. Okay, so I go 3 to 2 to 4. I keep going until I land at the place I want to end. And this gives me I did some examples. I get the cost of my shortest path directly from matrix A. So if I just want to know what's cheapest, I can just use matrix A, and it does Dijkstra's algorithm for all the vertices, not just one. I like that part, but it was not short. Finding the actual path requires me to use this second P matrix. Now, when I did this problem in the computer science class, it didn't exactly give me small graphs. Instead of using infinities, it used dashes. A 7 by 7 matrix means 350 steps by hand. So you know what I told the students to do? Code it. Do it in your own piece of Python, C, R, I don't care. Give me the code, give me the output. People, if I Google Floyd-Warshall algorithm, the first thing that comes up is an algorithmic calculator. You know what it asks me to give it? A drawing. The second one says, just give me the starting matrix. I like that one. Because I don't need a picture. That tells me everything about it. I don't have the graph. But that tells me everything about the graph I need to know. So that's sufficient. Several pieces of code that I got worked flawlessly. And several pieces, I have no idea what the hell happened. But I ran them all, and some of them worked. But then finding the path wasn't as obvious. How did you trace your way through P? I could get the costs fairly quickly. Getting the actual path without drawing the corresponding picture was the harder part of this. Do I expect you to be able to do this? Oh, hell no. But this is a major improvement in networking technology. Network, in this case, meaning a weighted digraph, not networking like, hi, how you doing? This is the way in which we can actually find not just the cheapest, but the actual path to follow. This is in miniature what Google Maps does live with traffic information. What your GPS does when it says, hey, traffic ahead, recalculating. It found you a shorter time route. It's using the weight of time. Why? Because there's an accident up ahead and you're... I drive down to Florida, I hit I-95, trust me, the damn thing says recalculating every 5 minutes. I hit I-77 outside of Carolinas, it's like, there's no other road, you're just gonna have to sit through it. We can't get you off here. South Carolina, there's a stretch of the road that just literally goes down the edge of the coast. And I have two choices. I drive down this interstate or I go into the ocean. My van doesn't float. It's not happening. I would love to tell you that this is an obtuse and obscure application of graph theory. But you see it all the time under the surface. Things you wouldn't otherwise imagine. Yes, sir. Again? It's usually the most efficient in terms of fixed networkings. For networks with variability in them, there are some other behaviors. There's a dynamic version of this that can be written up differently. And I'm absolutely sure that because this is an old algorithm, that there have been improvements made since. But this is the basis for all of it. I'm not going to say modern technology is absolutely using this algorithm, because I've never worked for a GPS company in my life. But I wager it's not that far off. And I'm sure it built on this. I remember most distinctly Bell Labs and AT&T when they did an improvement calculation on phone routing to route landline conversations before cell phones were a huge thing. They needed more switching stations. They said, where should we build them to be most efficient? And what should we reroute from and to? They paid, I'm going to these numbers up, somewhere around $11 billion for a 3.5% improvement in efficiency. They made their money back in 3 years. UPS did this. Have you ever seen a UPS or a FedEx driver make a left? They don't. If they can avoid it, they never make left turns. Why? I have to turn across traffic. I got to wait for the cross traffic to stop. I got to wait for a light to change. Even if I come up to a red light, I can make a right turn on red in most places. Faster and therefore more efficient to make 3 rights instead of 1 left. How would I have known? The shortest path takes me to right turns. So a block pass, make a right, make a right, make a right. You've now made the left turn. You didn't have to stop. And if, by the way, there are other stops along that right turn route, then I've dropped those off before going to the left. I thought it was bizarre that I was driving in the last time I taught this, the morning of, and I ran into a FedEx truck trying to make a left. Dude, have you been paying attention or not? Other questions? I will answer any question you have about the final exam on Monday. I would like you to bring your technology on Monday. I will give you some time at the beginning of class to ensure that everyone has the opportunity to fill out their course evaluations. Because I found out that so far only about half of you have. Go do that. I will see you all on Monday. Have a wonderful weekend.